Okay, welcome back, everybody. This is the final part of the Algebra 2 marathon. So, grab your notebook, grab a pen, pencil, anything you want to write with is fine. And we're going to tackle the last leg, which is going to involve a combination of skills and at the end some new functions called conics. All right, let's get started. So here we have a thing that looks kind of quadratic. If you can't read that, I'll just make this a little bit bigger for you. We have 2x to the 2/3 minus x to the 1/3 minus 15 equals 0. And this is quadratic because we see that this is three terms. That's kind of a good hint too. And we see that the powers on the variables going up. In fact, it doubles. So this is a quadratic indeed. We just have to make a substitution. We're going to substitute that u, or a, is equal to x to the 1/3, which makes this expression a very simple quadratic, which can be factored. So here we have 2u, here we have u. I guess this is going to be plus 5, and this should be minus 3. Yep, that'll give us what we want. You can FOIL that to check it out. And so we have 2u plus 5 equals 0, meaning u equals negative 5, and then divided by 2. Here we have u minus 3 equals 0. Sorry, I usually use a different color for the solution parts, but I'll just kind of... But we're not done. We're not solving for u because u stands for something. You stand for something. Whoever you are out there, you stand for something. U stands for x to the 1/3 power, which is the cube root of x, by the way. So in order to fix this, we need to cube both sides, which means multiply it by itself, That means by itself, and then by itself again. So negative 125 on the top, 2 times 2 times 2, 8 on the bottom. If you want to call that, what is that, negative 15.625, you can do that. It's totally up to you. And then here we have x to the 1/3 is equal to 3, so cubing both sides is pretty easy there. It's just 3 times 3 times 3, which is 27. So these are our answers in x. We needed to solve this with x values. Apparently, if you plug those in to this original equation, that will be a true equation. Okay, find the sum of the roots. It's very important that we're doing the sum of the roots, not just finding the solutions, but we're actually trying to find the sum of the solutions. Okay, so let's see if this factors. We have 3x squared plus 10x minus 5. This doesn't seem to factor. So what we can do is we can do a little trick here, which is going to save us some time. Instead of using the quadratic formula, x equals negative b plus or minus square root, all of that stuff, we can take advantage of this simple fact. If we divide everything by 3, I know that doesn't seem to make the equation nicer. Plus 10 over 3 minus 5 over 3. It actually looks like it's tougher. But in this format, you want to remember, what does FOIL multiplication really look like? If we have x minus r1, where that's the first root, and x minus r2, where that's the second root, the two numbers need to add up to be 10/3, and they need to multiply to be negative 5/3. In fact, that's what we do when we set up this x method and say, like, let's see what two numbers multiply to this and what two numbers add together to this. We're literally finding these two numbers based on that property. So if we reverse the property, we can realize that really we're just adding these two roots up to 10/3, and that's it. Now, what about the 3? The 3 is not really there. It's not relevant, because if we were to divide both sides by 3, like divide by 3, the roots would not change. The solutions would not change. For example, I could now totally multiply the equation by 7 on both sides and just put a 7 here. 7 times 0 is 0, so it stays 0. And that doesn't change what the roots were to make this inside 0, because this quadratic inside is like its own separate factor. Okay, I took the time to explain that because this is going to come in handy more than one place in this exercise. So the sum of the roots is this value, the b value, and the product of the roots is this constant term. Okay, Now, let's look at number 80. 80 says, given the graph of y equals 2x squared minus 3x minus 2, there's the graph. It's a parabola because it's the graph of a quadratic. Determine the coordinates for the point P. And if you can't see that, point P is very nicely, in fact, I even tried to bold it a little bit. It's very nicely on the x-axis. So we're really just looking for the 0. So let's just set this equal to 0. I believe we can solve it with factoring quite easily. So what multiplies, see, we're using that trick again. What multiplies to -4 and adds to -3? If I had divided the 2 out, these would all be cut in half. And so, yeah. Let's see, that's going to be, well, of course, -4 and +1, which means we can factor this with some grouping. 2x squared minus 4x plus x, minus 2. Group factoring, we're going to take this group, remove a 2x, and that leaves you with x minus 2. Of course, we're just going to take a 1 out of this group, and it also leaves you with x minus 2. So we have 2x plus 1 equals 0. That's going to give us probably a negative. Oops. And we have x minus 2 equals 0. So this gives us a -1/2, and this gives us a 2. Point P is clearly in the positive side of things, so this one is going to be 2, and then this one is going to be -1/2. So point P is at x equals 2. The coordinates are going to be 2, 0, because it's on the x-axis. Okay, great. Let's move on to the next, what we got up here. Find the value of k so that this line through the points given has k in it, by the way. You see that it's P is k, 3, and Q is 4, 12. So we want it to have a slope of -3, which basically means we can set up the slope formula. 12 minus 3 over 4 minus k, that needs to be equal to -3. So we have 9 over 4 minus k equals -3. And if we multiply 4 minus k on both sides, this cancels it on the left side. But when we multiply 4 minus k on the right side, we get -12 plus 3k, right? And so we get 21 equals 3k, which means k is 7. All right, so if k is 7, that seems to make sense, because then from 4, we would go down 3 to 9, then go down 3 to 6, and then go down 3 again to 3. So yeah, k equals 7. Ah, yes, the roots of this equation. Take a look at this. Find the sum and the product of the roots. This is very easy to do with one little trick first, because we see these radicals. Let's divide everything by negative radical 3. Okay? Yeah, we're going to multiply by negative radical 3. I'm going to move everything to the left side, which might be a bit of a shocker. I know you're like, what? You never put the leading coefficient on the side where it's negative. Why are you doing that this time? Minus square root 27x. There's a little bit of a method to my madness. I'm basically just going to show you something that works no matter what side you put things on, which is useful, right? Maybe you don't want to always put it on the positive side like I do. So what you can do here is you can divide everything by the leading coefficient, whether it's positive or whether it's negative. You can divide, in this case, by negative square root of 3, leaving us with x squared negative square root 27 over negative square root 3 is positive square root of 9. That's a nice number. It's 3. And then positive square root 12 divided by negative square root 3. That's going to be negative square root 4, but it has a better name, 2. All right, there we go. And so we do not have to solve these. There's no point in solving this. We just know from the property discussed before that if we were trying to factor this, for example, we would be asking what two numbers multiply to make -2 and they add together to make +3. Well, we don't have to find those numbers if we're simply trying to find the sum and product, because the sum and product is already injected in our question. That means we know that this must be the product, and we know, right, that this must be the roots. Right? Does that make sense? Like if we had some x minus r1 times x minus r2, what would they multiply to? Well, they would multiply to x squared minus 2, not 2, minus their sum, r1 plus r2, x, and then plus r1 times r2, right? If you FOIL it, that's what you will get. So we know that the sum is going to be negative 3. Oh, which means there's a mistake in this other problem, sorry. Right, this sum needs to be negative 10 over 3. There we go. Because when I use the roots as a factor, I'm not putting x plus r1 and x plus r2. I'm using x minus so that the roots are already present there. And that means, yeah, it's going to be the opposite of whatever term is there. Sorry. So yeah, let's get that rule correct, Mr. Tutor guy. All right, so as you can see, the product must be negative 2, and the sum must be negative 3. Great. Find a quadratic equation with integer coefficients and these following roots. This is a great example. So the sum of the roots, if I add these together, what do I get? I simply get 6. So this is going to be x squared minus 6x. Pretty simple. And then if I want to multiply them together, I can go ahead and do that. This is a difference of squares. A minus b, that's our a, that's our b, that's our a, that's our b. So we're just going to get a squared minus b squared, which is 9 minus 5 squared is 25, square root 3 squared is 3, 25 times 3 is 75. Pretty easy, right? Yeah, cool. Minus 66. That is the equation. Very simple. Using that property. Okay, now we're talking about something else with quadratic equations. We're looking for what value of k, or values, notice that makes the hint that there's more than one, will have exactly one solution. So you need to use the discriminant for this. I'm not going to teach you the discriminant in the 3 different cases here, but I'm just going to use it. We need to set the discriminant equal to 0 if we want exactly one solution. So we're going to have negative k squared minus 4 times 2 times 5. Again, if you don't understand why I'm doing this, you got to go study the discriminant. Make sure that you understand how I'm calculating these numbers, where I'm even getting these numbers from. From now, just accept the algebra now that we're doing. If you don't know the equation, that's okay, but I've plugged it in. And now we have to follow through with solving for k, which means we're going to take a square root here. Whenever you take a square root to solve an equation, you must have a plus or minus. Okay, so we have 2 root 10 is possible for k, and also negative 2 root 10 is possible for k. Those are our k values. There was more than one. Okay, great. Find k so that the equation x squared plus kx plus 3k minus 5, they use a really weird description here that you might not be familiar with, is tangent to the x-axis. Well, tangent means it just sits on the x-axis. So it can be something like this with the vertex right on there. It could also be going downwards with the vertex right on there. Those are examples of quadratic equations whose graphs are tangent to the x-axis. In fact, exactly one solution from the previous problem, that is the same description, because a solution is where it crosses the x-axis, and if it only touches the x-axis at one point, then we were also talking about those exact same quadratics up here, which means discriminant also needs to be 0. But before I get plugging stuff into the discriminant, I need to check my a, b, and c. My a equals 1, my b equals k, and my c is this entire thing here, 3k minus 5. That is my c value, okay? So when I try to solve this, I'm going to get b squared, which is k squared, minus 4 times 1 times 3k minus 5 equals to 0. And now I have a quadratic equation, but with k, which is kind of interesting. So distribute the 4. The 1 doesn't do anything. When you multiply 1, it just doesn't do anything. Plus 20. Okay. Talking about the k, okay. So here we have k minus 10, k minus 2 as the factors. Therefore, k can equal, I'm going to go back to using the brighter color for the final answer. K equals 10 and k equals 2. All right. 86, under what conditions on A, B, and C, what conditions, that's what we're looking for, on A, B, and C, will this equation have no real solutions? That is a different description of the discriminant. We're going to need the discriminant to be negative in that case, which simply means we just have to write out the discriminant. So here's the formula, in case you didn't realize it, is less than 0. The description for why the discriminant is useful in certain ways and how it indicates one solution or no solutions, that's something that you have to look into yourself, or maybe you have another video. Not sure. If I have another video about it, I'll link it in here, but if I don't have one made yet, then I guess I won't. Okay, simplify. This is I to the 119th power. So we're back talking about the i's. And they want us to write it in this form. Okay. I to the 119. Remember that the value of I, it cycles depending on what the power is. So it starts off as I, but I squared, for example, is -1. And based on that, I to the 4th is +1. And so if we take out the highest power of 4, the highest multiple of 4 from the power, which would be 116, and then we're left with I squared, and then we're left with I to the 1, because if you multiply these things, you're adding the exponents together, and it goes back to 119. This is equal to 1 times -1 times I. Therefore, it's just equal to -I. If you want to put this in a plus bi form, you can, but it looks kind of weird saying 0 minus I. I think -I is fine, but if they really want it with the number part and then the imaginary part, then I guess that's how we'll write the answer. Okay, simplify. Well, these are negative square roots, so they act the exact same as positive square roots. We just have to multiply by I at the end. So this is square root of 10 times square root of 50. They both have a negative square root, so it's times I, or in other words, times I squared. And we have the square root of 500 times I squared, which is 10 root 5, if we pull out square root of 100, which is 10. And since I squared is -1, this is just negative 10 root 5. Now, if they want us to write it as negative 10 root 5 plus 0i, we can do that. It's just kind of weird to do it, but we can do that. It's also acceptable. Okay, simplify. Interesting. In this case, we can simplify by dividing, but we don't use long division or simplifying like reducing the fraction. We have to fix the denominator, which is currently 2 plus I. In case you can't see that, give this a shot if you know what to do. You're going to have to multiply by the conjugate, the complex conjugate of the bottom, which is kind of like the evil twin, 2 minus I. And what that's going to create is it's going to create a difference of squares, because now you can see we have like an a plus b times a minus b situation. Therefore, in the bottom, we're going to get a squared, which is 4, minus b squared. We'll change that in a moment, because I squared is -1. Let's work out the top. This is going to be 8 minus 6 and minus 4 makes minus 10i. And then we're going to have plus 3i squared. Okay, again, I squared is -1. So really this is minus 3, so 5 minus 10i. And on the bottom, this is 4 plus 1, which is just 5, because I squared is -1. Oh, and this does reduce, so 1 minus 2i. That's the form they wanted in. This time we have a real and an imaginary number for it. So if it didn't reduce like this, like let's say it was like 6 over 5, or 6 minus 10i over 5, if they wanted it to be written in that very picky format, you would not reduce the first one, but then you could reduce the second one if you wanted to, or something like that. That's just an example, because this reduced very nicely. Both of them were divisible by 5. Or if it were like, I don't know, say 6 minus 3 I over 18. You know, you could reduce them differently. That's totally fine. Yeah. Okay, number 90. So this kind of a problem, which is an inequality, is going to be best approached with the method that I use called the chart. I'm not going to explain the chart. I'm going to use the chart here. The chart is very useful for determining when a factored expression is positive, negative, or zero by analyzing each of its factors individually. For example, if I plug in x equals 1, this would be positive, this would be positive, and this would be 0, so my whole product would be 0. It would not be greater than 0. If I plugged in a different number like x equals 2, these would all be positive, and so my result would be positive. If I plug in a number like x equals 0, this would be positive, positive times negative, and so my result will be negative. So the way to keep track of all of this stuff is to put it on a chart. Here we go. This is how you construct the chart. The top is a number line, and the number line is going to contain all of the zeros of each of the factors. So we have negative 7 makes this one 0. X equals 1 makes this one 0. And nothing makes this 0, actually. Did you know that? Because x squared is always greater than or equal to 0. So if I add 5, it's definitely going to be bigger than 0. Okay, so here's my first factor, x squared plus 5. I'm going to write it in this row, and it's going to have either positive or negative, depending on what the value is. Now, this is always positive, so I put pluses across the board. On the top number line, I need negative 7, because that's going to make my next factor 0. And then I need on my number line, on the top is a number line, x equals 1 for my factor x minus 1. That's going to make this 0. Now the pattern for this is very simple. Anything to the left is negative, anything to the right is positive, and my result of the product goes in the bottom row. It's going to be the result of positives times negatives. If anything is 0, of course, like if this factor is 0 because x equals negative 7, then of course the product will be 0 as well. If x is 1, this factor down here is 0, so the whole product will be 0. But other than that, we're comparing regions of x values. So anything to the left of negative 7 is a positive times a negative times a negative. Just look at the rows. Positive times negative times negative. That gives us a positive overall. Then for anything between negative 7 and 1, we have a negative. And for anything that's bigger than x equals 1, we have a positive times a positive times a positive. That gives us a positive. So we were looking for where the product is overall going to be positive. That's going to be located when x is less than 7, so anywhere from negative 7. And also whenever x is somewhere between positive 1 and infinity. Okay? So that's when this is going to be positive. Let's take a look at the next one here. The next one has 4 terms, so this smells a lot like grouping. It's probably going to be some group factoring. Usually 4 terms is a good clue for that. We can take x squared out of the first 2 terms, the first group, and that leaves us with 5x minus 3. We can take a negative 4 out, and this will also leave us with 5x minus 3. And we want this to be greater than 0, which means we want x squared minus 4 times 5x minus 3 to be greater than 0. Okay, now of course we can factor this one even down. In the chart, I believe, show you how to deal with quadratic factors like this, but if you can break it down more, of course, break it down more. And again, we want to know when this product is greater than 0, which means we need our zeros of each factor. So x equals 2, x equals negative 2, and x equals, you add 3 and divide 5, so 3 over 5. All right, let's put this on a chart. On top is the number line. Make sure you order these in the right order, least to greatest, and leave a little bit of space in between on this number line, just so you have spaces for the pluses and the minuses. Now the first factor, I think it was x minus 2. The next one is x plus 2. So this 0 is here, and this 0 is here. Incidentally, it would, in this case, still come out the same, even if you mix those up, but try not to mix those up in general, because they can be very different, depending on what the factor is. And here we have a 0 here. So like I said, if you were to accidentally mix some of these up, it actually wouldn't be the worst thing. You would still get the same answers, but it's good to keep track of the factors properly, individually. Okay, so anything to the left, negative on each of these factors. Anything to the right, positive. And that makes sense. Look at x minus 2. Let's look at the first factor for y. I'll give you a quick rundown. If x equals 2, obviously that's 0. But if x is less than 2, if you have less than $2 and you pay $2, you have negative dollars now. It's pretty simple. So if x is less than this, you're going to have negative as a result. The same logic applies for all of these. 5x minus 3. If I have less than 3/5, then when I do this operation, I'm going to have negative dollars, basically. Okay, so overall, we're going to have zeros here, and here, because each factor can contribute a 0, which would make the whole product 0. Anything to the left, you'll see this nice alternating property. A little trick is that you can just count how many negative signs there are, and if it's an odd number of negative signs, it's going to be negative. Like right here, 3 negative signs, it's negative. 1 negative sign, 2 negative signs, so when it's even, it's positive. Little tricks like that are cool. Okay, so whenever x is between negative 2 to 3/5, and also union 2 onto infinity. Okay, let's move on here. Oh, we got another inequality. This is not purely multiplication here. We have a division going on. Let's find the zeros. Of course, you know that the rule for a fraction is the denominator must never equal 0. So x equals negative 2 is kind of extra special. X equals 3 is the 0 there. This one is add 1 over 2, so 1 over 2. And we want to know when it's less than or equal to 0. We didn't have that before. We just had strictly greater, which is why in our intervals, we did not include the -7 and the 1. See, it's round brackets, not hard brackets. Same thing with this one. We want to know when it's strictly greater, not equals. We're not allowing it to be -2 or 3/5. It's with a boundary, a little curved boundary. Otherwise, we would have these hard brackets. So in this one, we're going to have some hardy RDR brackets. Okay, let's write our important points, our zeros of the factors. We have -2, and then 1/2, and then 3. This is going to give us x minus 3 as a factor. This is going to give us 2x minus 1 as a factor. This is going to give us x plus 2. And I'm going to put a star here. You're special because weird stuff happens when u equals 0. Instead of product, I'm just going to put like the result because we're dividing in some case. When this bottom factor is 0, we put bars as the result because that means undefined. If the denominator is 0, if anything in the denominator, like a factor, is 0, then the overall product is undefined, or the overall result is undefined. The rest of the things are the same, and the pattern of the sign behavior is the same. So like the negative positive behavior, it still applies the same way. If you have less than -2, right? If you owe more than $2 and someone gives you $2, you still have negative dollars, unfortunately. So let's do the pattern: negative, positive, 0, negative, 0, positive. And I'm specifying those zeros because we want to know when it's less than or equal to 0. So negative or equal to 0 is okay. Now here we have from negative infinity to -2. This is not a bracket because there's nothing at -2. It doesn't give us 0 as the overall result. But we're going to include bracket 1/2 to 3 because it does include those spots. Okay? All right, great. Solve over the complex numbers. Oh, that's suggesting that we're going to have some kind of a I situation, like imaginary values situation. Let's see if that's the case. You might notice that this is the opportunity to substitute. Let's call z squared, let's call it a. And therefore this is a squared minus 11a plus 10. That's way easier to factor and solve, right? This is going to give us a minus 10 and a minus 1. Yeah, pretty straightforward. Don't forget the z. Z's hanging out. Yeah, and so, I mean, we can put these back now if you really want to, but we could also just straight up solve for a, both of our a's. We're going to get a equals 10, a equals 1, but remember, a stands for something. It stands for z squared. So z squared equals 10, and z squared equals 1. And z equals 0, of course, is that solution. But let's solve more closely. That means z equals plus or minus, we're at 10, and z equals plus or minus, well, square root of 1 is just 1. So in total, we have, what are these little marks? So in total, we have z equals negative root 10, positive root 10, negative 1, 1, and 0. Those are our answers. No complex numbers, or no imaginary numbers, I mean. Interesting. This one might have it. In fact, I recognize this one. Solve over the complex numbers. Yeah, I think we've done this one. Let's divide everything out by negative 2, but we don't want to divide everything by negative 2z. You don't want to divide the variables out of the equation. Let's just divide everything by negative 2. So z4 plus 27z. Let's factor out a z, and that leaves us with a sum of cubes. Beautiful. This is our a cubed. Z cubed is our a cubed, and 27 is our b cubed. So the way that we factor this is just going to be a plus b, z plus 3, times a squared minus ab plus b squared. And if this all equals 0, remember this is going to be an irreducible quadratic, which means we can't factor it. It might have radical solutions, like square root solutions. Okay, this of course is just going to be z equals 0. This one's just going to be z equals negative 3. Not too bad. But for this one, we have to use the quadratic equation. So z equals 3 plus or minus square root of 9 minus 4 times 1 times 9 all over 2. So z equals 3 plus or minus the square root of 9 minus 36. And we can fix that by putting an I and also taking out square root of 9. So there are some factors. So altogether we have z equals 0, negative 3. We have 3 plus square root of 3. Sorry, there are a lot of 3's here to keep track of. 3 plus 3 square root of 3i all over 2. And 3 minus 3 square root of 3i all over 2. And you can feel free to like break those up a little bit if you want. All right, interesting. We're done with the quadratics for a moment. Let's look at these lines. The lines x minus 2y and 3x plus y equals 3 halves intersect at the point AB. Intersect, what does that mean? That means same location. In fact, they're even giving us the fact that it's like at a point, that this happens at a single point. They are the same. So let's go ahead and solve this. I'm going to show you a fraction busting method here. Let's just multiply this whole equation, both sides, by 4 to get rid of the fractions. 4x minus 8y equals negative 5. That looks way easier. And then let's go ahead and multiply this one. I can multiply it by 2, but you know what? I have the idea to multiply it by 8 so that the y's will cancel. It's a good idea. Multiply it by 8, and you get 24x plus 8y equals, okay, if I multiply this by 2, I just get 3. So if I multiply it by 8, I get 3 times 4, which is 12. And now I can add those equations together. Very simple. To get 28 equals 12 minus 5. Oh, 28x, that is. So x simply equals 1/4. Now that I know that, look at how easy it is if I use this equation. That's why it was kind of a good idea to bust the fraction. 1/4 times 4, it's just going to be 1, minus 8y equals negative 5. So that means that 1 minus 8y equals negative 5. Do the switcheroo. Switch places here. We're going to add those things on both sides and get 6 equals 8y. So y equals 6 over 8, or 3 over 4. And that means that the point where they intersect is 1/4, comma 3 over 4. And that's all they wanted to know, is like, what point does it intersect? Oh, nope, that's not all they wanted to know. Good to read the question every time. What's the value of a plus b? So it's just going to be 1. Yeah. Always good to read the question. Oh, let's move over to the last bit. The very last leg. You're almost there. It's time to talk about conic sections. We're back in quadratic land. So to identify what kind of conic section, we have 4 conic sections: the circle, the ellipse, the hyperbola, the parabola. To identify a conic section by this equation, we want to check the highest exponents. They both have, you gotta go look at your conic section equations to confirm all this. They have the same squared, but they have opposite signs and different numbers. So because they have an opposite sign in front, this is a hyperbola. And we'll see that it fits the equation x minus h squared over a squared minus y minus k squared over b squared equals 1. It needs to equal 1. So let's simplify this. I know that's pretty complicated. Let's simplify this by completing the square. So let's get all of our x stuff over here. Let's leave a little space. And then let's get our y stuff over here with the negative 25 factored out. So here we have y squared left, dividing out by 25, or negative 25 is pretty much the process for factoring. And then let's leave a little space. And with 234, it can go on the other side. We don't need it right now. The method for completing the square, you should remember, is to divide by 2, divide the b value by 2, and square it. So we need to add 16. And on here, we need to add 9. But we need to balance that on the other side of the equation. So here's plus 16. And we're not going to do plus 9 because we didn't really do plus 9, right? We did plus 9 inside of these parentheses, which are being multiplied by a negative 25. So in reality, we did plus 9 times negative 25, which is negative 225. So we have to balance that by subtracting 225. Okay, this is just keeping it balanced, nothing crazy. And now we can turn these into perfect square trinomials. We can factor these perfect square trinomials. And here we're going to have y plus 3, and that is squared. So we're going to end up with 234 minus 225, that's 9, plus 16, that's 25. And remember what format we need this in. We need to divide this by 25. Divide everything by 25, divide everything by 25. And so here we have the correct format, x minus 4 squared over 5 squared minus y plus 3 squared. You could put over 1 squared if you'd like to. It'll help you graph it. Equals to 1. So the way we graph this is we locate the center at h comma k. Oops. H comma k is going to be 4 along here, 3 down. There's our center, which isn't actually a point on the hyperbola. In order to find that, we have to use the number below the x to stretch it by 5 this way, and stretch it by 5 this way. Now where does the 1 come in? The 1 comes in because there needs to be sort of this boundary above and below by 1, and we draw these sort of diagonals through the center like that, and these diagonals are going to kind of asymptotically guide. They're going to basically get approached. They're like these lines that we get closer and closer to with the hyperbola, but we never actually touch. Okay, so that 1, what did it do really? It controlled like how wide this is. You know, if it were like a 2, then the boundaries would have been a little further out, would have been wider. Okay, but definitely review your conic section so that you're familiar with what I'm talking about here. Now let's identify the next kind of conic section. This is going to be a situation where they both have positives, but they have a different coefficient, which means we have an ellipse on our hands, which is basically like an oval. It's a glorified oval. Really, a circle is just a special type of ellipse. So let's use the same methods. We have to separate the x stuff and the y stuff. You'll notice that this is already perfect for the y stuff, so I'm just going to leave that as y minus 3 squared. But on this side, I need to factor the 9, and I'll have x squared minus 2x. That one, I'm going to complete the square. So I'm going to cut the negative 2 in half, and then square it. That should give you positive 1. But I didn't just add positive 1, right? I added positive 1 times 9, because it's inside of these parentheses. So on the other side, I have to add 9. Pretty straightforward. Now, let's condense this to a perfect square factor as well. That's x minus 1 all squared plus y minus 3 squared equals 9. And we need this to be in the format quite similarly to the hyperbola, but not exactly the same. One key difference is this plus, which is how I was able to identify this as an ellipse rather than in a hyperbola, because they had both plus, whereas in the hyperbola, one had plus on the squared and one had minus on the squared. This one had both plus. Okay, let's divide by 9 to finish this off. And this is going to give me x minus 1. You can go ahead and put it over 1 squared if that helps. Plus y minus 3 squared all over 3 squared equals to 1. And again, just like the hyperbola, the center point is not actually on the ellipse. It's just a reference point of like where the center of the egg is. It's kind of like an egg shape. Sometimes I call it an egg. And then if we look at the stretch individually on the x, that's 1. So we're going to have a point that's like 1 to the left and 1 to the right. And on the y, you look at the stretch, and that is 3. So we're going to go from the center. Everything comes from the center. That's kind of why we use the center, because just like in yoga, everything comes from center. And we can draw our ellipse, or kind of, oops, it shouldn't dip into that space. This should be like the outermost point. There we go. That looks acceptable, I guess. Honestly, I probably wouldn't be happy about that, but I think it's because I scaled my axis pretty weird. This is pretty far out. Let's fix that. My OCD is kicking in, guys. I'm sorry. Actually, my center is off center. You don't want your center to be off center. Okay, this looks a little bit more symmetric, at least. That's a rough sketch of what it would look like. Got it. So identify what kind of conic section. This time we have a nice one. The x squared and the y squared are positives, but they're also the same value. So this means that we have a circle on our hands, okay? Yeah. So what we're going to do is we're going to gather this. This is going to be y squared minus 4/3 y, which is a little tricky to deal with, but it's going to be okay, promise. Then we have 9x squared. That one's just chilling, just waiting. And to complete the square, we have to divide by 2, which means we're going to have 2/3 now, negative 2/3, and then square that, which gives you positive 4/9. See, it's not so bad, because this is not really adding 4/9. It's adding 4/9 times 9, which is just 4. So if you add 4 there, we're going to have 9x squared plus 9 times y minus 2/3 squared equals 9. Very nice. Divide everything by 9. And now we have the equation of a rather small little circle, centered at x equals 0, y equals negative 3/2. Maybe I'll make this a little bit larger for emphasis. And the radius is simply 1. So we're going to go out to like here, going to go out to like here, 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 something like that. Yep. And again, the center is not actually on the circle, but oh, and we should also identify it as a circle thingy. Okay, here we go. It's pretty much the final stretch, everybody. Write the equation of the circle in standard form, given a radius of 2 square root of 2, and the center Oh, here we go. The center is at the intersection of these 2 points. Okay. So where do these intersect? Well, we can find that out by simply multiplying this equation by 3. 9x plus 3y equals 3. And 2x minus 3y equals 4. Therefore, 11x equals 7, which is not the nicest set of numbers. 7/11ths. It's not really all that nice. So this is going to be our h. It's going to be our center location, because the circle equation is going to be x minus h squared. So we have x minus 7/11ths squared plus, now let's go find the y value. If we want to find the y value, I think what I'm going to do is I'm going to take these two equations. I'm going to multiply this one by 2. 6x plus 2y equals 2. You can do whatever you want with equations as long as you do the same thing on both sides. And then I'm going to multiply this by 3 and get 6x minus 9y, is that right? Yeah, equals 12. And then I'm simply going to subtract these. So negative, positive, negative. That's going to give me 11y equals negative 10. So y equals negative 10 on 11. All right. So now we're going to have y minus negative 10 on 11, or in other words, just, positive 10 on 11 squared. And what do we do with this radius? Remember, the equation for a circle has r squared, and so this is just going to be 8. Pretty nice. So we had to use the intersection of these two lines to find the center location. Yeah, in fact, I can kind of sketch that a little bit because these are in a nice standard form. So I know that the y-intercept, for example, is 1, and that the x-intercept is 1/3. So here is that line. Now for this one, I know that the x-intercept is 2, and the y-intercept is, let's see, negative 4/3, which is like down here. And so there is the center of the circle, and the circle is going to be, if I'm guessing, I'm kind of guessing at this, it's going to be something like that. You can graph these if you'd like. You can graph these two equations, and even graph the equation of the circle on Desmos or something, and it'll show you that. Find the line of symmetry between the 2 points. Interesting. So if we have 2 points here at negative 3, 2, and at 1, negative 4, we want to find the exact symmetrical line, which is going to cut this in the middle. See that? I drew the line segment connecting them, and I really want to know the slope of that line. Okay? So the slope of that line is going to be y2 minus y1 over x2 minus x1. Be careful with the negative. When you subtract a negative, it becomes a positive. So 1 plus 3 is 4, and that slope is negative 3/2. But you'll notice that the line of symmetry, you might remember this from geometry, it is a perpendicular bisector, which means it cuts it in half, but it's also perpendicular. It makes a 90-degree angle. Those are pretty good perpendicular bisectors. So we have to find the perpendicular bisector to the segment that is the line of symmetry. And we can just find the midpoint now. The midpoint between these points is going to be negative 3 plus 1 over 2, that's for the x, and then 2 plus negative 4 over 2, that'll find you the middle of the y's, and that'll give you negative 1, negative 1, which is kind of looking like where I drew it. It's not too bad. It's a little off. Therefore, the equation of this line is simply y plus 1. If we put this in point slope form, y minus y value, so y plus 1 equals negative 3/2 x plus 1. Yeah. Okay. We want to reflect the point 2, 1 over the line y equals 3x. So here's that line, y equals 3x. Oops, that's definitely not the line. That looks about right. And here we have the point 2, 1, like that. Okay, not too bad. So we'd like to find sort of the midpoint here. I wonder if we can just switch the x and the y, except the x we would switch with Yeah, so it'd be like 1 for the y, but we're switching the x to 3x. Sorry, what I mean here is 1, which is the y value, becomes the x value, and 3 times 2, which is currently 2 is the x value, is going to turn into 3 times 2 for the y value. I'm curious if that works. I don't believe it does. Seems like it would be somewhere here. Okay, I guess I'll stop trying to guess. So if we have some point, which is the midpoint, right? What is the coordinates of the point? This is x comma 3x. And we want to find that is the midpoint. So that means that 2 plus something, we'll call it a, over 2 equals x. And 1 plus something, we'll call it b, over 2 equals 3x. Okay, this is helpful. So we have that 2 plus a equals 2x. And we have that 1 plus b equals 6x. Well, how else can I relate a and b, right? I also know that the perpendicular bisector is this line 3x. So that means that the slope of the line segment connecting these two is going to be a slope of negative 1 over 3, right? So negative 1 over 3 is going to equal 1 minus b over 2 minus a. And that's really going to help us because we can take these equations and we can basically replace them. Yeah. Okay, so here let's work things out a little bit. We're going to have, if we cross multiply, we're going to have a minus 2 equals 3 minus 3b. And then we can simply replace the a here if we'd like to, right? We have that 2 plus a is 2x. So that means a equals 2x minus 2. So this is going to be 2x minus 4 equals 3 minus 3 times b. What is b? b is just 6x minus 1. Minus 3 times 6x minus 1. So here we have negative 18x plus 3 plus another 3 equals 2x minus 4. Add the 18x over, so 20x equals 10, and therefore x equals a half. Well, if x equals a half, we can now find the y value, right? How can we find the y value? Well, we can use the slope. We can say y equals negative 1/3 x. I guess we don't know the plus b. Huh. How should we do this? How should we find the y value? Well, the y value is just b. Yeah, so we can just use this equation over here. Okay, b equals 6x minus 1. That's what we should use. Yeah, no need to overthink it. So 6 times a half is 3 minus 1, and it just goes to 2. Okay, so that means this point goes to 1/2, comma 2. And that does look a lot more appropriate as being the reflected spot. Yeah. Okay, let's move on. Oh, I think this is the last page, everybody. Yes, it is. Okay, great. Excuse me. Find the center, radius, area, and circumference. Okay, these are just going to come as a result of the radius. Once you have the radius, you can find that. So let's take this equation and complete the square. Get all the x stuff together, plus 6x. Get all the y stuff together, plus 10y. And make sure that we're cutting in half and then squaring. Cut it in half and then square it. So we're going to need to add 34 on this side. And that gives us perfect squares. And this really easily shows us where our center location is. That means we have a center location of negative 3, comma negative 5. And the radius, the equation is r squared. So the radius is square root of 34. Negative 3, comma negative 5. Square root of 34. The area is simply pi times r squared, so 34 pi. It would be units squared. And the circumference is simply 2 pi r, so this would just be 2 pi times square root of 34, which I think you would just leave like that. You can't really simplify square root of 34. It's like it's a little more than 58, but it's a little bit less than 59. I mean 5.8, it's a little bit less than 5.9. Given the two lines, find the equation of the circle that's centered at their intersection. Okay, and it passes through the origin. So one of the points is 0, 0 on the circle. All right, now let's find where these intersect in the first place. So here's 2x plus 6. We could just plug that in. So 4x minus 2x plus 6 equals 8. That means 2x equals 2, which means x equals 1. Great. That's the center location of the circle. And if x equals 1, then that means y equals 2 plus 6, which is 8. Okay. That seems weird. I see what I've done wrong. It's good to catch some of these things. I didn't distribute the minus properly, so it's negative 2x minus 6. So we get that 2x equals 14. Got it. Which means x equals 7. Yeah, very, very important catch there. And if x equals 7, that means y equals 20. That makes much more sense. I was trying to plug it into this equation as well, and it wasn't working out. So if it doesn't work in both equations, then, there's a problem. You made a mistake. So here's the center location. This is going to be x minus 7 squared plus y minus 20 squared equals r squared. Now there's a couple ways to find out the radius here. We know that it passes through 0, 0, so that means that the radius, let's say this is 720. We know that it has to reach this point. And if we want to know that distance, and then the circle's just kind of like, this whole thing or whatever. It's a pretty bad circle, but something like that. If we want to find that radius, we can just make a right triangle out of this, where this is 7, this is 20. So therefore, 7 squared plus 20 squared equals r squared. We don't even need to take the square root. We can just use that because the equation uses r squared. Unless it asks for the radius. No, it just asks for the equation of the circle. So 449. All right, nice. Okay, find the domain. Interesting, the domain of equations. This is important, and it's a quick run through. This is the final stretch for real this time. Any polynomial will have a domain of all real numbers. So you could put all real numbers, or you can simply put from negative infinity to infinity. There are no restrictions on a quadratic. Okay. 105, find the domain. This one is different. This one has two restrictions. We have the rational restriction, which means there's a fraction. Remember, the denominator cannot equal 0, so x cannot equal 1. But also for a square root, we can't have the inside of a square root be negative, so x plus 4 must be greater than or equal to 0, which means x must be greater than or equal to negative 4. Must be. And so we're going to take a numbered line, and we're going to say everything greater than negative 4 is fine, including negative 4, except for when we get to 1. There's like a little blip at 1, and everything else is good. So the way that we write that in interval notation is bracket negative 4, comma 1 with a parentheses, union 1 to infinity. Basically, as long as x is bigger than negative 4, we're good, but there's a little blip at 1. Okay. And here is the last problem, everybody. Oh my god. Find the domain of the given equation. We have both a rational situation, and we also have a square root inside of there. So first of all, because of the square root, x must be greater than or equal to 0. But because of the fraction, 3 minus square root of x must not actually equal 0, which means 3 must not equal square root of x, which means 9 must not equal x. So as long as we're bigger than 0, we're good. And then there's a little blip at 9. but then we continue from 9 to infinity. It's all gravy again. Okay? And that is our domain, and that does it, everyone. That is the marathon. Look at all these pages. We did over 100 questions. I hope you found some of this stuff helpful. Of course, go back and review these, all of them. I doubt you remember every single question, so go ahead and solve them a second time. Watch this as many times as you need. And like I said, I'll be providing a link for the video with the chart on this as well. Thank you for joining. See you next time.